Okay, so you might have to press a button saying that's okay. All right, here we go. So I'm sharing my screen, and the one I am sharing is this one. Okay, so this is about Form 4 and radioactivity, and it's an important topic. They don't ask a lot of questions about it, but the questions are quite easy, which is why we're doing it now. Okay, that's just the reason we're going to do it, because the questions are quite easy, so you don't need to be very good at it to be able to get good marks. So firstly, we're going to talk about the reaction, the types of radiation which we have. You probably know this, but in case you don't, here we go. When they started looking at radioactivity and radiation, that's Henry Becquerel and the Curies, Madame Curie and her husband, they found that there were three types. And the three types were affected by electric charges differently. So if on the left we have a radioactive source and we pass whatever is coming out of it between two plates, and one is positive and one is negative, then some of the particles were attracted towards the negative, and that showed they were positive. Some of them were attracted towards the positive, which showed they were negative, and some of them went straight through. Now, actually, this diagram is not very good. This is a diagram which comes from a KCSE textbook, but I'm going to change it a little bit. So I'm going to show you a different way of drawing it. So I need to show you this one. Okay. So I'm going to make this just a little bit bigger. Okay, so here's the diagram, and I'm going to tell you what's wrong with it, because sometimes they ask you to draw this diagram for alpha, beta, and gamma particles, which are the three. Okay, so here we go. So the thing which is wrong with this is that the one which is attracted to the negative, so the negative is down here at the bottom, okay? One of them is attracted towards the negative, but actually, although it is attracted towards the negative, it is not very attracted. So it goes sort of this a rubbish diagram, but it's more like that. The one which is attracted towards the positive is very strongly attracted and moves a lot. In other words, this line here is wrong. Now that's really quite important. You need to know that the one which is attracted to the negative, the one which is positively charged, is not as strongly attracted, apparently, as the one which is attracted to the positive. Okay, that's very important. Now, the reason for that is that it's to do with the mass of the particles. Okay, so we're going to go back to the other original share, and it's very important that you see that. So in other words, on this diagram here, the one here which comes down towards the negative one should be less bent. So it should still move towards the negative, but it should hit around about here somewhere, okay? Not right down at the bottom. Now, you probably know that the ones which are attracted towards the negative are alpha particles, the ones which are attracted towards the positive are beta, and the ones which go straight through are called gamma rays, not particles. So alpha and beta and gamma are the first three letters of the Greek alphabet: alpha, beta, gamma. Alpha are positively charged and move towards the negative. Beta are negatively charged and move towards the positive. And the gamma, which are not particles, which are rays, just go straight through. Okay? Okay, I hope that's okay with everybody there. That hopefully will make sense. So, as I said, if we had the diagram drawn properly, then the ones which are the gamma, where am I? Gamma should go basically, should go straight through. Okay. The ones which are beta will be bent up really a lot. And the ones which are alpha are bent, but not as much as the beta. Okay, so if you were going to draw it, then that's important. That's how you would draw it. Okay, so alpha attracted towards negative, beta attracted towards positive, and gamma rays, so alpha particles, beta particles, and gamma rays. Okay, so that's how you would draw it if you were asked to. I know my diagram is very bad, but that's what it looks like. That's the first thing. So three types of radiation: alpha, beta, and gamma. So you need to know how much they can go through things. And basically, alpha particles are stopped very easily by just a piece of paper. So alpha particles hit a piece of paper and cannot get through. Beta particles can get straight through the piece of paper, but are stopped by aluminium foil. Okay, so aluminium foil, less than a centimeter in thickness, will stop beta particles easily. Gamma rays will go through paper, aluminium, concrete, but will be stopped by a few centimeters of lead. Okay, stopped by a few centimeters of lead. So alpha particles, paper, beta particles, aluminium foil, gamma rays, only lead, straight through concrete, unless it's very, very thick. Kibera Glory, I'm glad you're enjoying smacking his head, but let's focus on some chemistry as well. When they started looking at radioactive chemicals, they discovered something called half-life. And half-life is a very simple idea. And it goes like this, that something which decays by radioactivity in a certain amount of time halves the number of the original atoms. In other words, if I start with 100 atoms here up at the top, and it goes down to 50 atoms, then the time that it takes to halve that will be the same as the amount of time that it takes to go from 50 down to 25, from 25 down to, you can't go down to 12.5 atoms, but that's, if we were doing this in grams, 100 grams to 50, 50 to 25, 25, and so on. It's given the symbol T1/2, okay? T with a half underneath it as a subscript. Okay, T1/2 is half-life. Now, this is a very important idea, half-life. And what you need to know is that it is not affected by the sort of things which change reaction rate. You are sometimes asked about the difference between radioactivity and a chemical reaction. You probably know that the rate of a chemical reaction depends on things like temperature, concentration, and so on. But radioactivity cannot be changed by physical methods. In other words, it doesn't matter if we heat it up or cool it down or get more of it, the half-life will be constant. Now, some half-lives are very, very, very long and some are very short. So here are some examples. So uranium-238 takes 4.5 billion years to halve its amount. 4.5 billion years. So if you have some uranium, you have a problem, because although the uranium-238 is not actually very dangerous, it is going to be around for a very, very long time. Whereas polonium-210, 210 polonium here down at the bottom, has a half-life of 2 to the minus 4 seconds, 2 10,000ths of a second. Gone. So in other words, we have to be aware that the half-life is very different depending on the different, what we call nuclides, the different radioactive or radiochemicals. You never have to remember these, but we have to be able to use them. So carbon-14, which is used in trying to find out how old something is, has a half-life of 5,600 years. So if I had 10 grams of carbon-14, guys, Silver Spring, I'm having to mute you, sorry. If I had 10 grams of carbon-14, after 5,600 years, I would have 5 grams. After 5,600 more years, I would have 2.5, then 1.25, and so on. Okay, it's very important that you understand that it doesn't matter what the half-life is, it means the same thing. Now, whenever a radioactive chemical decays, what we call decays, it can do it by losing alpha particles, beta particles, or gamma rays. And it depends on why it is trying to lose things as to which one it does. But this is what we're talking about. So here's an example. If we have a very heavy atom, that is, it has many, many protons and neutrons, the fastest way it can be stable is to lose the helium particle, the helium nucleus particle, what we call the alpha particle. We'll go through what that is. We'll be able to write some equations in a minute. But if an atom is too big, very big atoms usually use helium, loss of helium nuclei, alpha particles, to become more stable. Now, when a radioactive chemical decays, it may decay into another radioactive chemical. It doesn't become stable necessarily after the first decay. That's an important idea. Excuse me. So you start with a radioactive chemical. Maybe it's got a very, very big nucleus, and it starts to decay and it loses an alpha particle, and it forms a new chemical which may not be radioactive, but it might be radioactive. So the idea is that we need to know what is happening and what is formed and whether it is radioactive afterwards. So when it loses a helium nucleus, it loses the 42He2+. That is an alpha particle. An alpha particle has a mass of 4, a proton or atomic number of 2, and a 2+ charge. It's the helium nucleus. In other words, helium atom should be 42He, but it's lost its 2 electrons, so it's He2+. Okay, so an alpha particle, 42He2+. If you lose a beta particle, it actually produces 2 particles, but the one that we concentrate on is this one. This is an electron. And at this level, in physics we shouldn't, but in chemistry at the moment, we can ignore this second one, and we just write a beta particle as though it is just an electron. Don't bother drawing this. This happens usually when there are too many neutrons. And there are too many neutrons. What's happened is we lose an electron. And the reason for that is this. If we lose a neutron, it sounds funny to lose a neutron. What actually happens, basically we change the neutron, is that one neutron turns into a proton and a beta particle, which is basically an electron. So that means because neutrons and protons weigh the same, that the atomic mass will not change. So the mass has no change. But the proton number, because we've lost a neutron, the proton number increases. Now that's really strange. So when we lose a beta particle, the mass doesn't change at all, but the number of protons increases by 1 because one neutron has become one proton and the beta particle which disappears. Okay, so the proton stays in the atom. Okay. Radioactivity by gamma ray, by losing gamma rays, is not is something which is a little bit different because it is for very energetic atoms, atoms which are often artificially energized by us, and they lose gamma radiation, but it doesn't change the mass number or the proton number. Okay, so there's no change to the mass number or the proton number. Now, in a decay series, we call the first atom, we call it the parent isotope. And the parent isotope decays into daughter isotopes. Sometimes they are stable and sometimes they are not. So let's just have a little bit of a look at this one, because this is a good example of the sort of thing that happens. So this is TH, which is going to decay, and the TH will decay into Ra, and they change. So TH is thorium and Ra is radium. And then radium is going to change into actinium. And you don't need to know their names. But what we want to look at is just the numbers. Okay, it's the numbers that matter. So we're going to look at it on a different sheet. So 23290 thorium is going to change into 22888 radium, which is going to change into 22889 actinium. Okay. So that's what we're going to look at. So I'm going to share a different screen. So I'm going to go to a different screen. So here it is. Okay. I'm going to try and write on it and try and show you what is actually happening. So what you've got to concentrate on is the actual numbers, what is happening to the individual chemicals. So let's just write down what we've got to start with. So we've got thorium, and it's 23290. And we are told that it turns into, nothing hits it first, it just changes into Ra, radium, and that is 228 and 88. Now, something else we know because it says here, but something else is formed. So what you do is you say, okay, I don't know what it is. I'm going to call it X. And I just look at this and I go, okay, 232 has become 228. That means that this must be 4, and 90 becomes 88, and therefore that must be 2. Then you have to go, okay, I know what X is, because X, I get rid of the X, X must be the helium nucleus. Don't forget the 2+ charge, it's really important. You could write 4,2 beta, whoops, sorry, not beta, no, not beta at all. You could write 4,2 alpha. You don't need to put the charge on an alpha, okay? You could write this, but this is better. Okay, so all we did was we looked at the numbers. 232 becomes 228, and therefore that's 4. Okay, 90 becomes 88, and therefore that's 2, because the two sides of the equation have to add up to make sense. Then it decays again. So that's how we know what was formed there. So then it decays again. Oh, I better have my product. Actinium. So now I have Ra, and it's 228, 88, and it turns into actinium, which is 228 and 89. And something, well, I don't know what it is. Well, I do exactly the same again. Okay, so I'm going to change my colors. I'm going to go, okay, from here, 228 to 228. Oh, there's no change. And therefore, the number that goes here must be 0. And if I look at the atomic number, it's going from 88 to 89. Well, that's a bit strange. It's got to add up. So 88 equals 89 and minus 1. Well, that's weird. Ah, that's because X must actually be an electron. Now, the electron has a 1 negative charge, which you have to remember. You could write 0 minus 1 beta, got it right this time, and you don't need the charge, but it's better to write this, okay? So again, all we're doing is we're looking, okay, 228 turns into 228. Oh, so that's got to be 0. 88 goes to 89. It's gone up 1, so this has to add to this to make 88. So it's 88 equals 89 plus negative 1. Okay, I hope that makes sense. So let's go back to our other screen. Is that okay so far? Is that okay? Everybody okay? Cool, excellent, very good. Silver Spring, is that okay? Good, well done, thank you. So we're going to go back to the other screen. Let's go. So all we do is we look at the individual atomic mass, atomic number, see what's happening, decide what has happened. Now, this is what we call natural decay. We can make decay happen artificially by adding something to the parent isotope. So we can, and it's often neutrons, we often attack a radioactive element with neutrons, but we're not going to deal with that today. This is a decay series, and you may have seen these graphs before. The important thing to recognize is that there are really only 2 types of arrow on this. There is one that goes diagonally from right to left, diagonally, and there is one that goes from left to right, here, across. The numbers along the bottom are the atomic numbers, so 81 to 92 here, and up the side is the mass number. Let's look at this a little bit more closely. So let's look at this one here. So here we have uranium-238. And uranium-238, I've got the numbers down the side. I hope you can see them. Let me just move this out of the way. Okay. So uranium, the numbers, the mass numbers are around down the side here, 238, 234, 230, 226. So to go from uranium-238 to thorium-234, the mass has gone down by 4. And if we look at what has happened to the atomic number, it has gone from 92 here in this column to 91 and 90. So the proton number has gone down by 2, okay? It's gone down from 92 to 90. Now, that means that it has lost something which is 4 at the top and 2 at the bottom. That's the alpha particle. So it helps if you get used to these, that the one, every time it goes diagonally like this, that is an alpha particle. Every one of these diagonals, every one of them, alpha particle, alpha particle, alpha particle, alpha, 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 alpha. Okay, every single one of those is an alpha. The ones which go straight across, if you look at it, there is no change to the mass number, to the atomic mass. Okay, so these here, THPAU, okay, thorium, palladium, uranium, these are all 234. but thorium has 90 protons, palladium has 91, and Pa is proactinium, not palladium, and uranium-232 is number 92. So if it's going across, the mass number is not changing, but the atomic number is going up by 1 each time. That is a beta decay. So every time you get a horizontal line left to right, that's beta decay. So beta, beta. So if we follow this down, uranium to thorium, that's an alpha. Thorium to proactinium, that's a beta. That's a beta. Alpha, alpha, going down to radium, down to radon 222, that's an alpha, another alpha, another alpha, ending up at lead. Lead then goes across, so that's a beta to bismuth. Bismuth to polonium, that's a beta, etc. Okay, so that's how it works. Diagonals, alpha, horizontals left to right, betas. Very important that you remember that. Okay, so let's have a look at some. Now it's time for you to have a go. Okay, I want you to have a go at this. So what I'd like you to do is just to write down some of these. Oh, that's interesting. They made an error here. Let's see if I can change it. No, I can't. Oh, hello. I can't change it. Sorry. That there should be TH. Doesn't matter. So what I want you to do is to see if you can write an equation for U turning into TH, that should be TH, and then TH turning into PA, and PA turning into U, and U turning into TH. Okay, just do the 1, 2, 3, 4 stages. We'll look at them in just a minute. Just see if you can work it out. Talk to your neighbor. See if you can agree on what has to happen. Just see if you can look at the numbers. So you're going to write 23892U goes to 23490TH, should be TH, plus something. And then 23490TH goes to 23491PA plus something. Okay? Let's have a go. See if you can do it. Oops, sorry. My apologies. Hang on. Here it is. Sorry. So just have a go. See if you can do a little bit of it. Just a few steps. St. Mary's, show me again, please. Hang on, let me just make you bigger. Hang on. Let me just make you bigger. Hang on. Hang on. Oh, come on. Well done. Now, the 4-2 should be what? What should the 4-2 be? You're right that U turns into TH and it's a 4-2, but what should the 4-2 be? Show me again, St. Mary's. Show me that again, and we'll just have a look at it just for a minute. Okay, so you're right with your arithmetic. Yeah, absolutely right, but it's not PA. It's not PA. So what is it? Just think for a minute. What do you think it is? That's very good, Asharika. Hold it a bit closer again, please. Just a bit closer again. Asharika. Oh no, Asharika have gone. Oh, that's annoying. I hope everybody's getting this a little bit. Asharika have disappeared, which is a bit of a shame because they got a good answer there. Let's just have a look at it. So there's some of it. I hope I've got this on a different sheet. Oh, what is happening? Ah, yes, here we are. So if I just write on this, I'm just going to write across this just for a minute. Okay. So if I look at this, go on, that's fine. So if I look at this, it goes from 238 to 234. So this one will lose something which is 4 at the top. 92 goes into 90, so it's 2 at the bottom. And as soon as you get 4, 2, you should just write HE 2 plus. In the next one, so we would write 238 92U goes to 234 90 TH plus 42HE2 plus. In the next one, 234 goes to 234. So the thing which is lost is 0 at the top, but 90 goes to 91. That means the thing at the bottom must be -1. And that means it's an electron or a beta particle. In the next one, it goes 234 goes to 234, and 91 goes to 92. So again, it's 0 and -1, which means it's an electron. In this one, going down to thorium again, it's going to lose a 4, and then 92 down to 2 down to 90 is 2. So that's another alpha particle. Okay, so we would actually write it as, like in this very first one here, we would write 238 92U turns into TH, which is 234 90 plus either alpha or beta 42 HE 2 plus. Okay, I hope everybody gets that. Okay, so that's how you write them. Okay, let's go back to the original. Go back to the original. Here we are. So I hope you would be able to look at any part of this and say, okay, from bismuth to polonium here, it's 240. This is, I'm in the middle down towards the bottom, 21483. Here, bismuth goes to 21484. Ah, that there, that's a 0 -1. That's an electron or a beta particle. So what you need to do is look at what happens to the mass number, the proton number, and decide. Then the mass number, the proton number, and decide. Okay, simple stuff. So here's some questions. Here's some questions with the answers covered up. Okay, with the answers covered up. And I'm going to just ask you to have a look at some of these. Oh, there was one thing. Sorry, I'd forgotten something. So I'm just going to go back one. One of the other questions is about half-lives. They often ask questions about half-lives. So I'll just do one here. Okay, so let's say that we have a radiochemical X, and it has a half-life of 26 days. Okay, 26 days. And let's say that we start with at the start, we have 10 kilograms. Then how long will it be before we get down below 2 kilograms? Okay, how long before mass is less than 2 kilograms? Just see if you can have a go at that. Just see if you can do that. It won't be an exact number of days. It will be more than such and such. Okay, it's not going to be, in this case, it is not going to be an exact number of days because we haven't plotted it, but some of you may be able to do it very well. I might make it easier just this time to start with because we haven't done one of these before. So let's make it a bit easier. Let's make it 1.25 kilograms. Okay, let's make it 1.25 kilograms. Okay, I hope that's starting to make sense. So the idea is we just go, okay, if I've got 10 kilograms to start with, I know that to go from 10 kilograms, if I've got 26 days, it will go to 5 kilograms. If I have another 26 days, then it will go to 2.5 kilograms. Another 26 days, and it will go to 1.25 kilograms. So if it asks how long before the mass gets to less than 1.25 kilograms, then it is 26 and 26 and 26, which is 78 days, and it's more than 78 days. Okay, it's going to be just over 78 days. Is that okay, or do you want another example? Would you like to do another example? Thumbs up if you would like another example. Okay, let's do another example. Does everybody understand that? Are we okay on that one? Is that okay? Okay. Let's look at the questions I've got. Hang on. I'm just looking at a question. Okay. So, okay, so here we go. Let me just go back to my proper screen. So here's a real KCSE question. We have a chemical X, has a half-life of 25 days. Okay. After 100 days, its mass equals 20 grams. What is, or was, the original mass? Okay, so after 100 days, it's 20. So what did it weigh beforehand? If its half-life is 25 days and it decays for 100 days, then what must it have weighed to start with? So we want to know how many grams over 100 days gives me 20 grams. So what's this? So if we've got some answers, show me. I'd like to see a really great answer. That would be really nice. Anybody got an answer? Oh, somebody at Silver Spring got an answer? No? Anybody got an answer? Anybody got an answer? Somebody's got an answer. Oh, somebody at St. Mary's? No, yes, no. Yes, we have an answer. We have an answer. Oh, no, hang on. Hang on. You have done something, you've done something about right, but the wrong way round. If it's getting it's ended up at 20, so what we want to know is how much it was at the beginning. That's true. That's, oh, hang on. That would not kilograms to grams. Right, nearly right, nearly right. Let's just have a look at it. I'll do it in just a moment because we do want to move on. Just remember, each 25 days, its mass halves. Okay, so I'll give you a bit of a hint. Okay, so I'll try and give you a little bit of a help. In other words, if it ends up as 20 grams after 25 days, because 25 days is its half-life, the time that it takes to halve the amount, that before the 25 days, it must have been 40 grams. So what would it have been before that? Because 100 days is 4 times 25 days. In other words, it's 4 half-lives. Okay? So the time, which is 100 days, divided by the half-life, which is 25, is 4. So it has halved 4 times. So to end up at 20, it went 40, 80, 160, 320 grams. So 320 down to 160 is 25 days. 160 down to 40 is another 25. 80 down to 40 is another 25. And 40 down to 20 is the last 25. So your 100 days is 4 half-lives. And so it has halved 4 times. Okay. Okay, the other things you need to know about radioactivity are you need to know some uses of radioactivity. They quite often ask about things like, just give me 2 ways that radioactivity is used. One is in hospitals killing cancers. Okay, they use many radioactive isotopes to kill cancers. Like if you had a brain tumor, they would use a gamma ray to kill the tumor because they don't want to go in cutting your head open. Okay, so in hospitals, they use radioactivity. In food, they kill bugs using X-rays. Okay, so before they put beans in a tin, they X-ray it. That's important. They use it to find out what is happening in your body. All right, so those are some uses. The dangers of radioactivity you need to know. And so you need to know that, for instance, if you worked in a nuclear power plant, you would have to wear protective clothing, which means you don't breathe the air, and your suit is lined with lead, and you are behind concrete and lead glass, okay? Just to stop the radioactivity getting to you. So it's very useful because it produces a lot of energy. And the last thing is you need to know about fission and fusion. Fission means breaking. Natural radioactivity is always about breaking. Fusion is about putting atoms together. What happens in the sun? In the sun, atoms of hydrogen are forced together to make atoms of helium, and that gives out a lot of energy. Now, you may know that in countries like the US and UK and Germany, they are trying really hard to make fusion work because there is nothing bad left over. Hydrogen makes helium. Easy, great. There's nothing bad left over. Most nuclear power plants produce very radioactive, very dangerous chemicals. 2 examples. You may remember that in Russia, there was a nuclear disaster in 1986, and there was another one in Japan in 2006. Okay, so they were both disasters, and they both released a lot of radioactive elements into the air. So that's the end of radioactivity. That's the end. That's all I'm going to do. All of that stuff you should be able to do okay. So we're just going to go back and run through it very quickly. Okay, so the things you have to remember. Firstly, alpha particles are positively charged, so they're attracted towards negative. Beta particles are negative, so attracted towards positive. Beta particles are, oh, I should have said, beta particles are curved, their path is curved more because they are much lighter. They have much less mass, whereas alpha particles are difficult to turn because they are heavy. Gamma rays go straight on. Alpha particles are stopped by paper, beta particles by aluminium foil, gamma rays only by several centimeters of lead. Half-lives, that is the time for half of the original atoms to disintegrate. So it doesn't matter what mass we end up with, we start off with, it will take the same amount of time each time. In this case, from 100 down to 50 takes a time of 2. By the time we get to 4, we're down to half. By the time we get to 6, we're down to half. It's 2 days or hours or seconds or whatever it is in this case. You have to know they vary a lot. This one, 4.5 billion years. This 20,000ths of a second. We can lose alpha particles, which are He nuclei, 42He, 2+. We can lose beta particles. They are like electrons, well, part of them are electron, 0, -1 electron. And gamma rays do not change the number of protons or the number of neutrons, and therefore the mass and proton number stay the same. These graphs you have to get to use. The diagonals are alpha, the horizontals are betas. You can write the equations from one to another just by counting, and you will be able to work it out. Okay? Here are a load of questions which I will send to your teachers, and here are the answers are on the next set of they're afterwards. Okay, so you can ask your teachers to go through these because all of the answers are at the end, or they can just get rid of the red box. Okay, so that's the end of radioactivity. So I'm going to do a very small amount on electrochemistry because some people wanted to do electrochemistry. Now, we did some electrochemistry when we did about the extraction of aluminium. The extraction of aluminium, pretty straightforward, really, quite simple. And one of the best pieces of information, one of the best ones to do a question on. But I'm going to go to electrolysis here. So here's a little bit about electrolysis, and I'm going to assume that you know some of electrolysis. You have to know about these things here. Sorry, I'll just move myself out of the way. You have to know about what happens. This is form 4 electrolysis, about what these diagrams mean and what happens, and why particular chemicals are produced in electrolysis. And you have to know about Faraday's law. Okay, that's what you need to know. The sort of questions you get are like this. This is the electrolysis of copper sulfate. Identify anode and cathode. Write the half reactions. Write a cell reaction. What's being oxidized and reduced and so on. And I'm going to do one just now. Okay, I'm just going to do one quite simply now. It is very useful for you to know the reactivity series of metals, and you need to know what oxidation and reduction means. you need to know what cation, anion, cathode, and anode mean. Okay, I always show to my students cation drawn with, instead of the T, a plus. If there's a plus there, you remember that a cation is positive, therefore the anion is negative, and cations go to cathodes, and therefore the cathode must be negative. The anode must be positive. So just by writing that plus in there instead of a T can help. Okay. So the sort of questions you get are like this. Here's some magnesium sulfate solution. Here's a power pack. And they ask you, what could the electrodes be made out of? And say what happens in the reaction. Here's another one. Name the electrodes. Okay. Say what is happening at A and B and so on. All right. So we're going to do one example like this. I'm just going to do one example, so hopefully it will make sense to you. So I'm going to look at copper sulfate being discharged. Okay, I'm looking at copper sulfate solution. So I'm going to have a beaker, and in my beaker I'm going to have 2 electrodes like this. They are going to be connected to a positive and negative electrode, and in here we will have some CuSO4AQ, copper sulfate solution. The first thing you need to know is which one of these is positive and which one is negative. I'll tell you that the long line is the positive one and the short one is the negative one. That's very important. The way I teach my class is that the long line is long enough to make the plus. The short one is only enough to make the minus. So copper sulfate solution will contain Cu2 plus ions, SO4 2 minus ions, and because it's in water, we have H plus and OH minus. So we need to know what is formed. So we're going to have Cu2 plus and H plus. Cu2 plus and H plus are the cations. Okay, and the cations will go to the cathode. So we need to identify the cathode. Now the cathode must be minus if the cations are positive. So this must be the cathode over here. Now that means that this one over here is the anode. That's good. That's easy. As soon as we've identified one, we've identified the other one. Then I need to know, and we did this a few weeks ago, the reactivity series of the metals. So I'm only going to do a few of them here. And you need to know that hydrogen comes in here. So this is the reactivity series of most of the metals. And when you're looking at electrolysis, you compare the 2 cations and you say which one is lower in the reactivity series, and that one will be produced. So it's not the hydrogen, it's the Cu2 plus. So the Cu2 plus, which is in here, will be attracted towards the cathode. So all of the Cu2 plus will be attracted towards the cathode. Now the cathode is negative, so it is full of electrons, lots and lots and lots of electrons. So what happens is that the Cu2 plus picks up electrons and becomes copper. Now to balance it, I need 2 electrons, but that means I get copper, and therefore the electrode, let's see if I can find an appropriate color, yes. the electrode goes copper colored. Okay, the electrode goes copper colored because we've got copper. Okay. Now, at the other electrode, we have SO42 minus and OH minus. And the rule is which anion is what we call discharged. And the answer is, if there's Cl minus, it's that. If no Cl minus, then it's the OH minus. But you need to know what happens with OH minus. What happens with OH minus is this. OH minus loses electrons to form water and oxygen. To do that, we have to balance it with 4 of those, which forms 2 of these. And it means because we've got the minus charge here, we have to lose 4 electrons. Or you can write 4OH minus turns into 2H2O and O2 and 4 electrons on this side. It doesn't matter. So in other words, here we get bubbles of oxygen coming off. Okay? So that's how we decide what is formed. It's quite a tricky thing, but that's how we decide what is formed. Okay? So in the cations, you look for the less reactive cation. In the list of metals, we look for the least reactive. So let me give you another example now. Here's another example. It won't be very long at all, I promise. I know it's nearly time to go, but I just want to give you another example. So let's say I change this, and this time I have a beaker. I have my 2 electrodes. This time I'm going to change the way round it's written there, like that. Oh, hello, that's tricky. And into here, I'm going to put some sodium chloride solution. So my ions are Na plus and H plus and Cl minus and OH minus. Which one is positive? Which one is negative? This one, the longer line, is positive. The shorter line is negative. Which of these is lower in the reactivity series? Sodium up at the top or hydrogen at the bottom? It's hydrogen. So the hydrogen is discharged. So the hydrogen here in the solution goes to the electrode, which is full of electrons. And the hydrogen ions pick up electrons and become hydrogen. Now, because it's H2, we would need 2 H's. And because we have 2 H's, we would need 2 electrons. So hydrogen bubbles are going to come up here. Hydrogen bubbles are going to come out. We're going to see bubbles up here. What about at the positive electrode? We've got chloride and hydroxide. In my example before, I said, whoops, sorry. Come here. Come on. Here, this is the key bit here. Hang on, let me just, it's this. If we've got chloride, it will be produced. If we have no chloride, it will be the hydroxide. So in this one here, where's it gone? Come on. In this one here, whoops, sorry, we have chloride. And therefore, we will get Cl minus loses electrons to become Cl2. So 2 of those and 2 of those, and therefore here we get chlorine being produced. Okay, so that's a really important example. Now, the only other question they often ask about these simple ones is the electrode material. And the electrode material is normally carbon. Okay, they sometimes say graphite, but it is basically just carbon. Okay, so if they ask you what the electrodes are made of, it is normally graphite. Okay, that's as much time as we have time for. If anybody has any particular questions and you want to stay for a minute and ask a question, another question about organic or something like that, then just wait for a minute and ask a question. But if not, and you want to go home, you go home, or you go and do something else, or go and get a job or something. Yeah, whatever you want to do, you go and do it. But if you have a question, wait for a minute. I hope that is useful. I know you have examinations next week, practice examinations, and then the proper ones. Good luck. I really, really hope it goes well for you. Keep thinking, look at the questions, read the question, be very, very careful. Read all the questions first. Don't let them trick you. So I will be here if anybody wants to ask a question for about another 10-15 minutes. But everybody else can go.